Okay, today we're going to start with 2 diploma release questions. And then we'll do a quick review, and 6.5 is just a small stretch from what we did yesterday, pun intended. Here's the first question. So unfortunately we can't see the whole thing all at once, but we have this wiper on the rear of a window on a car. We know the angle is 5 pi by 6, so we see that here. In a single sweep, it clears that region that's 16 inches wide, where you see that wiper blade. So there's that information. What we want to do is figure out the perimeter of the cleared region to the nearest inch. And I don't think we'll be able to see. Let's see. There we go. We can see the 4 options. See what you come up with. Okay, so there I've outlined the perimeter for you. And since I last mentioned that only 21% got it correct when it was on a diploma exam, a number of you have changed your answer, so let's see what we come up with now. Anybody vote A? Nobody's for A. B? C? One bold person. Oh, 2? No. D? Ah, D it is. So let's just review why it's D. Can somebody explain the process? Yes.
So I found the arc of the base circle.
Okay, so if we call that the arc, and what formula did you use? Or how did you? A over R. Okay. And let me call this A1 because we're going to have another arc there. So you found the arc was equal to the radius times theta. And so the radius was? 105 divided by 6. Well, let me do it in smaller pieces so I can catch up to you. So the radius is this full length, right? So the 4 plus the 16. So the radius is 20 inches, and that theta is 5 pi over 6. Which you said was what? 100 pi divided by 6. So that was the length of this arc down here. Okay. Then.
I found the arc of a small circle.
So A2 would be the radius, which is 4, times the angle, 5 pi by 6. So you get that is equal to 20 pi divided by 6. And then?
And I added the 2 arcs together, plus the 2 16 inches.
Plus 2 times 16, because this is 16 and this is 16 there. So you added that all up, and we do get 95 inches. Good, thank you. Yes? And something went wrong, because it does, 95 is how it rounds correctly. So, tricky question, standard of excellence, which I wasn't sure if it was going to be standard of excellence, but I haven't read the standards really recently, but it was considered a standard of excellence question. We're good? All right, next question. What you're asked to do is you're given a point that's the intersection of the unit circle and the terminal arm of 145 degrees for an angle in standard position. Now, ideally, I would say you should be able to answer this question in, well, I want to say 30 seconds or less, but I could say a minute or less. But today, because we're not done the chapter, we haven't studied and prepared as though we had a test today. So it may take a little bit longer. But once we kind of think it through what's going on, we should be able to do it fairly quickly. Now I say that knowing that I'm a slow processor. And if I was actually doing this on a test and wasn't a teacher but was a student, it probably would have taken me more than a minute. But here's the question. So when you have an answer, just give me a thumbs up in front of you so I have an idea of who's done, who needs more time. Thank you. All right. Who can tell me what they did? Look around. Artie, could you tell me? Okay. Okay, I'm going to have you pause there, just because people who are watching the video won't know what you did. So we have this diagram, so you suggested we draw the angle in standard position, and we find the reference angle of 35. Since it is the unit circle, we know the R value is 1. And then you said, oh, since R is 1, the value of x will just be cos 35, but we know it's negative because we're in the negative direction. Okay? And actually, that's all we really need to do. Because as you look at your x values, there's only one of them that has the negative 0.82. So we could have done it like that. Anybody do it a way that you'd say is faster? Lukman? Yeah. So remember, if we have a point on the unit circle, then the ordered pair is cos 145 degrees, sine 145 degrees, and we could just even plug in the cos 145, and that would give us the negative 0.28. Both work, and in the moment you do what comes to mind, but handy to remember that ordered pair because we have a unit circle. So that would have been a really fast way to do it that if I was the student, I probably wouldn't have thought of it. But having seen this question a number of times, now I say, oh yeah, it is that simple. But we learn through experience, right? Through seeing different methods. Any questions or comments? No. Okay. So here, I am going to give you a timer. 1 minute to sketch 2 graphs. And I'd like you to do it without looking at your notes. Ooh, if you can. And if you can't do this today, don't panic, because we just started looking at graphs yesterday. But I want to push us towards recognizing these graphs fairly quickly. So you should have a piece of paper handy. And what I'd like you to do, I'll wait till we have paper out, ready to sketch. Y equals sine x, y equals cos x. That was a minute. Not much time. But let me just go over what I will do because it's familiar to me. So what I would do is I wouldn't start by putting a scale on the x or the y axis. I'd start by just drawing my curve. And from yesterday, we saw that both of these are kind of a wavy curve. Sine x starts at 0, 0, and then curves up, down, and back up. And cos x starts at the maximum, curves down, and then back up. So we get the shape of the curve like that, and then I would look to say, well, what scale do I need? I know my maximum is 1, minimum is -1. If I think in degrees, yesterday we did radians, but I'll do degrees first. I know a period is a full time around the circle, 360 degrees. So this would be 180 degrees. That would have been at 0. And then similar idea for cosine. My maximum's at 1, minimum's at -1. A full period, let's think radians, once around the circle, is 2 pi. Halfway will be at pi, so that's where we're at the minimum. And then 0 is here, and let me fill in a couple more this time. This would be at pi over 2, so it's halfway between the maximum and minimum. And this one will be 3 pi over 2, again halfway between the minimum and maximum. So as we continue on in this chapter, we just want to get really familiar with these 2 graphs so that we could sketch them quickly, we understand them well, kind of the key features. Any comments or questions with those? Nope. Okay, so let's get into the lesson for today. And I'll have you begin with this warm-up question, just reviewing from chapter 3. What is each of these transformations that's happening to that function? All right, let's just quickly review these together. Number 1, Denise, number 1, how would you describe that? Vertical stretch by a factor of 2. Yes. Number 2, Muhammad. Yeah, horizontal stretch by a factor of 1/2. And number 3, Danny. Translation 2 to the right. Yep. And number 4, Iman. Translate 2 up. Yep. Perfect. So just to do kind of a quick overview of what we're looking at in this lesson, we'll look at Desmos, because today it's actually working. And I never do this reverse contrast, so I thought, is that okay to see? It's not as good, hey? This is probably easier to see. So what we're going to do is we're going to apply those transformations. So here, you'll see my red graph is a sine x. And if I change this a value, guess what's going to happen? If I make a bigger, what will happen to my graph? Yes. It'll get stretched vertically. So right now, what's the amplitude for this function? Yes, it is 1. So if I have a stretch factor of 2, guess what the amplitude is? 2. Yep. So if I bring this up to a 2, stretch vertically by a factor of 2, oh, there we go. It's twice as high vertically. And if I went to something smaller than 1, then we'd say it's stretched horizontally or stretched vertically by a factor of 1/2. So the amplitude is now 1/2. So whatever this number is multiplied in front of our sine function, that will tell us the amplitude. Almost. Because just like before, if I do a negative, it's a reflection. So we think of the sine is going to tell me if it's reflected in the x-axis, and then the size will give me the amplitude. So it'll be the absolute value of this a that'll tell me what the amplitude is. So if I went to -3, there we go. It's reflected, so the bumps that used to go up are now dips that go down, and it's stretched 3 times. All right. We'll bring this back to 1. Now, what's going to happen if I change this b value, if I make it bigger? Ooh. Rather than tell me in terms of transformations, I'd like you to predict in terms of the features we talked about yesterday. So yesterday we talked about amplitude for a periodic function. We talked about domain and range. So the amplitude will have changed the range. We talked about period, and we talked about where the zeros are. Those are some of the things we talked about. Oh, also the center line or midline. So talk to somebody close by you. What's changing if I was to change this b value to a 2? What's changing there? Amplitude, period, center line, translation. Hey, talk to your neighbor. Okay. Anybody volunteer to tell me what you think is going to change? Praveen? The period and the zeros. Okay. So if I change this b value to a 2, will the period get bigger or smaller? Bigger. So this is going to go smaller. So I'm changing it to a 2, and I think you're right, because it's getting squished horizontally. Oh, there we go. So the period is smaller. The period is actually half as big. So we see one complete cycle that goes up and down and back again by the time you reach pi radians. Okay, so that would be like a horizontal stretch, which is kind of accordion-like when we have this wavy thing happening. So the bigger our b value, the smaller our period is. And we could also do negatives for the b value, but we won't for this course. Sometimes we'll throw in negative a values, or if we're asked to write an equation, using a negative a value will make it simpler in some ways. It won't be required, but we'll talk about negative a values. Negative b values, not so much. Okay, we'll bring this back to there. And if we change the C, if I make the C bigger, what will happen to my graph? Predictions? I heard some mumbling. Volunteer? Yes? It's going to move to the right if I make this bigger. Yes, you're right, because we have that subtract C already in the equation. So the minus sign's already there. So this is going to move the graph to the right and to the left. And then as we look at the D value, what will happen is I make D bigger. Call it out, sure. Yeah, it's going to go up. That was an okay call. Only this big of a call. And I didn't really give you much warning, but yep, there you go. It's going to go up, going to go down based on the D value. So that's pretty much the lesson for today. Question? If we switch the variables, we would get the graph of the inverse. Yes, we would. But we're not going to look at graphs of inverses of these. So, yeah, there are notes. But, well, and there's some terminology. So I should run through at least the terminology initially, and then I'll have you fill in some of the details. So first of all, here in our notes, question 5, if I have 2 times sine x, we would say it is a vertical stretch by a factor of 2. And the key feature we want to highlight is amplitude. That our A value will give us the amplitude. And I'll give you a little bit of time to fill in the rest of this in a couple minutes. But now I'm going to skip on to the next one, which is the next page. If I have the sine of 2x, then we'd say it's a horizontal stretch. And the key thing we're looking at here is it changes the period. And so I suppose I should be sketching these. Okay, so it's changing the period, stretched by a factor of a half. So that 0 times a half is still 0. This point at 2 pi times a half will be pi, so I have a complete period by there. If I was to sketch this, that's where I'd start. And as we look at the graph of sine x or cos x, we can kind of think of it as having 4 sections, kind of like the 4 quadrants we go through. So let me just talk about the original function. If I think of it as having 4 sections, there's the end, there's halfway, there's a quarter, and 3/4. So the things that are happening are kind of in those 4 sections, I get 1 complete period. At each quarter, I get either a maximum, a center line, or a minimum. So those are the points that I get when I come to sketching the graph. So if it's stretched by horizontally by a factor of a half, I know my full period is up to there. So I'm going to divide that section between this red dot and this red dot into 4 sections. So there's a half, there's a quarter, there's 3/4. Because sine starts on the center line, halfway in between, beginning and end, it'll be on the center line again. It starts by curving up, so it'll be at a maximum here, and it'll be at a minimum here. So this would be 1 period for my graph. And then I would just keep that pattern going. So it'll be at a maximum, center line, minimum, and center line. Okay, let me go back to the previous one because we didn't sketch this graph, but we should sketch it. Vertical stretch by a factor of 2. The zeros stay where they were, the minimum and maximum values will be twice as far from the x-axis, so we'll be up there and down here. So this is the graph that we would get for y equals 2 sine x. Change in amplitude. Number 6 was a change in the period. Number 7 is a horizontal translation with a periodic function. We call it a phase shift. So even though we're looking at transformations kind of the same as we did in chapter 3, we have some special language that we use. So rather than vertical stretches, we'll talk more about how the amplitude has changed. Rather than horizontal stretches, we'll talk more about how the period has changed. Rather than horizontal translations, we'll talk about phase shift. And then for vertical translation, for some reason they pick vertical displacement. We'll get there in a moment. So phase shift means this whole graph is moved to the right pi by 2, which means the point that used to be here will be half a pi, or pi by 2 to the right. So what I do is I kind of find my first point, and then I just count grid lines and say, oh, so every point is 3 grid lines to the right. And then that's just simpler for my brain. I don't have to think about the scale so much anymore. So my maximum is 3 to the right. My next point on the center line, 3 to the right. My minimum, 3 to the right as well. And then if I use this pattern, I can predict what's going to happen for that section of the graph that I didn't draw, which is that I'll need to have a minimum here, which is part of the graph that shifted over as well. Okay, and those descriptors I'll let you look at in a little bit. Finally, we have this vertical translation or vertical displacement, which would be 1 unit up. And here, what we're going to focus on is how it affects the median, so that center line. So when I'm going to sketch the graph of a transformed sine or cosine function, I like to start with where's the location of my center line. And then I'll think about some other features. So I'll think about, has there been any horizontal translation? No. Which means my graph starts on the y-axis on the center line, or on the median. I ask, is there a change in the period? Nope, period is 2 pi, which means my graph ends here on the center line again because it's a sine function. And then I divide it up into the 4 sections. Halfway between those 2 points on the center line, I'm also at the center line. Halfway between those first 2, it goes up to a maximum. The amplitude hasn't changed, it's still 1. Halfway between the next 2 points on the midline will be at a minimum. Amplitude is 1, so I'm going 1 unit down. And there's my graph. All right. So before I give you some time to fill in these characteristics, no, I'll give you time for that first, and then we'll look at this in general stuff later. So take the next few minutes, 10 minutes, whatever, to fill in the characteristics, domain range, y-intercept, zeros, amplitude, period, and median for each of these graphs, please. And then we can compare them in a little while. Quick comment, when you fill in the domains, don't just write the domain of as much of the graph as is drawn. Think of the entire function. So for this first one, if I just think of this, not necessarily what's been drawn, what's the domain of y equals 2 sine x? Let me just talk about this first one with you. Hopefully you got a domain of all real numbers. Any questions with that? Whether we were degrees or radians, we would say it's all real numbers. Range, our minimum is -2, maximum +2. It reaches those values, so we need the square brackets. Y-intercept is at the origin, 0, 0. The zeros are at 0, then pi, then 2 pi, 3 pi, 4 pi. And so I'm just saying it's going to be k pi, where k is an integer, so multiples of pi. Amplitude is 2 because of that vertical stretch. Period is 2 pi. That's the scale we were given in radians. And when we talk about the median or the center line, we always want an equation. So don't just say it's 0, but actually write the equation y equals 0. Lukeman. Yeah, the graph just goes from 0 to 2 pi, which is why I interrupted you at the start and said, just look at the equation. For this equation, what would the domain be? So not based on the graph that you're given. Any other questions? No? Okay, I'll give you some more time on the next few. Here's what I get for those characteristics for number 6. Anybody have a question with these? Yes. How do I figure out the zeros? So what I'm doing is, kind of as a general rule, what I'll do is I'll find the smallest positive 0 if I can, or in this case, it's right at 0. And then I'll look at what's the distance in between. So I'll say, well, there's my first 0. It's when x is 0. And then as I look at distances, I see it's 3 grid lines. 6 grid lines was pi, so this is at half of a pi. So I think of the scale that's written on there, and I see that's half a pi, and then it's going to be that same distance between all of these zeros. So I'm going to add on to that, basically pi by 2 times k. But typically, just my habit, it's not uncommon, I just stick the k in front and then say k would be an integer. And we'll do the same thing once we start having phase shifts. You'll just pick one of the intercepts and then you'll add multiples of the distance between them. So that'll come up in the next one. Any other questions with number 6? All right. Who has not finished number 7 yet? Most of us are done, so why don't I just go through it with you. Domain still all real numbers. By range, there's no vertical stretch, so still -1 to +1. The y-intercept, so now because of that horizontal translation, that phase shift, my y-intercept is in a different location, so it's at 0, -1. So my graph starts at a minimum. So again, here, just a reminder that we need to be careful with contexts, as in, this is an interval, this is an interval, this is an ordered pair. So even though they kind of look the same, the context is telling me which is an interval and which is an ordered pair. So these are both x values, those are all y values. This is an x and a y. The zeros. So here, I look at this point and say, well, that's my first positive 0. We could pick any 0. As kind of a math convention, typically we pick the smallest positive. If you don't, it's not wrong. So that smallest positive one, it's 3 grid lines. I look here and say, oh, pi is 6 grid lines, so this is pi over 2. And then I look to see how far apart are they. So from here to there, 6 grid lines, that was pi radians. So I'm going to add pi, but multiples of pi to it. So my zeros are at pi by 2 plus k pi, where k is an integer. Any questions with the zeros? All right, amplitude, still 1. There is no vertical stretch. Our a value is 1. Period is 2 pi, because our b value is 1. No horizontal stretch. And the median, still y equals 0, because there was no translation up or down. And I'll give you another couple minutes on the next one. Okay, let me talk about number 8 with you. So, key things changing here. Our range has changed because of that vertical translation. And the median has changed. It's y equals 1 now. But that also affected our zeros. So it's possible that we can have no zeros if it had been translated up further. It wouldn't intersect the x-axis at all. In this case, what we're seeing is we have one intersection point here. And so I see, well, there's pi, there's 2 pi. So that's halfway in between, which will be 3 pi by 2. But that's the only one within one period. So the next one won't happen until the next period. So I'm going to say my zeros will be at 3 pi by 2 plus a full period times k. Question? Yeah. I'm talking about zeros right now. No, that's okay. Yes, you are correct. I should fix that. You noticed it. That should be 0, 1. Thank you. Yes, I will give you a candy. Gwen, is that what you were going to point out too? Sorry. Zeros? Are we good with the zeros? Question? Well, I would say, so the question is 12 grid lines is one period. For this graph, yes. And for most of the graphs I've given you, yes. Will that always be the case? No. So you need to make sure you're looking at the scale. 12 grid lines is just handy because then every grid line is a pi by 6, which gives you the pi by 6s, the pi by 3s, the pi by 2s, and the pi's. So it gives you all the nice special angles except the pi by 4. Okay. Let's just look at this at the bottom of the page. This is taken straight from your workbook. So rather than retyping it, I just copied it out of there. So, first of all, cosine is basically the same idea. So if I have cosine of x minus c, then we'd say it's been translated c units horizontally. That would be a phase shift. If we have an a multiplied in front, we'd say it's vertically stretched. Again, your workbook uses the term compressed, but we won't, so that's why I've stroked that out. And again, amplitude is always positive. So if the a value is negative, we'd say it's a reflection, but we'd still say the amplitude is a positive number. If we have something multiplied to the x, then we have it stretched horizontally, which changes the period. And again, we just look at the absolute value of the b, just like we looked at the absolute value of the a. And then a number added to the end is a vertical translation, or a vertical displacement, we might say. But because the graphs are essentially identical, just shifted left to or right of each other, all the features do the same thing for cosine. All right. So hopefully, now that we've reached the end, You can sketch the graph of a single transformation, y equals sine x, cos x, without technology. So a single transformation, meaning any of these. So if I just have a vertical displacement, you could sketch the graph without a calculator. Same thing for just a change in period or just a change in amplitude. The next lesson just puts them all together. So it's kind of like what we did in chapter 3. We looked at each transformation separately, and then we put them all together to see what would happen. And then describing the characteristics when we have a single transformation. And there we go. That is this lesson. And just so I go on record for the people on video, because at this point it slows down, this feels a little more manageable, it's a good time to do some review. Make sure you're keeping up with the previous lessons. Alrighty.